let's come to the dry cell and the fuel cell part over here and continue the discussion there. All right, so when we talk about dry cell here, so I think it'll be best to go for the NCRT part of the dry cell over here. Do you have NCRT with you, Kana? You follow NCRT syllabus, right?
Yes.
Can you just send me a photograph of the NCRT syllabus's dry cell part? You have a textbook with you now?
Yeah.
So just send me the NCRT syllabus part of the dry cell and the fuel cells. Let's start off with this now. Let me actually take it to a fresh page and discuss this. So the principles we have discussed will all be followed in these two cells over here. We'll talk about them as we are discussing them from the NCRT directly, because this part here doesn't require too much understanding, but it requires information, which NCRT gives better. You're still on, right, Prisha?
Yes.
All right, so let's continue here. So let's dive into primary and secondary cells. So I'm assuming you understand what a primary cell and its secondary cell, the basic difference is correct. Primary cell is something which is not rechargeable. A secondary cell is rechargeable. Bluntly speaking, that's the difference. So a primary cell, you will end up having the reaction being possible only in one direction, which is the forward direction. Rather, to put it very simply, the reaction is controllable in that format only in the forward direction. Remember, what is the purpose of all of these cells? The purpose of these cells is to control a reaction at the end of the day, right? So in any cell, whether it's electrochemical or electrolytic, if it's an electrolytic cell, what are we doing? We are still controlling the reaction, but we are making the reaction happen there. In the electrochemical, what are we doing? We are controlling the reaction, but that reaction is doing something for us. Instead of we giving something to the reaction, we are taking something from the reaction. So the difference is, in the electrochemical cell, we take something from that chemical reaction. Whereas in the electrolytic cell, we give something to the, chemical reaction in that particular case there. In net essence, that's basically what happens. So in this particular case here, when you're going to be considering the, primary batteries over here, let's quickly have a talk on the primary battery here. What you can see over here is the primary battery is something where we can only control one direction, or the setup we have associated with that battery can control only one direction. Whereas in the secondary battery, the setup we will be having will be capable of having control over both the directions, over the electrochemical part and the electrolytic part. When you want to have a reaction, you can't just have one direction being one thing. If I have a particular reaction having one direction being delta G negative, opposite direction is automatically going to be delta G positive in that particular manner there. Which means if I want to do in one direction, I'll be gaining energy. In the other direction, I'll have to supply energy. So when you have a cell which is built in a manner where only one direction can be controlled properly, that becomes a primary battery. Something where it is built in a manner where you can control both, then you call it a secondary battery. Okay, so let's talk about primary battery and dry cell first over here. So dry cell here, the primary reaction which occurs, the reaction occurs only once, and after use over a period of time, the battery becomes dead. This is what I was basically explaining. It is basically what is meant by a primary battery here, and cannot be reused again. Wonderful. Okay. So in this case here, they are mentioning a few points over here. However, for a battery to be of practical use, it should be reasonably light, compact, and its voltage should not vary appreciably during its use. These are the main 3 points. Reasonably light, compact are both okay. But the other one, the voltage should not vary appreciably. That is a very, 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 very key point. It gets glossed over usually, but it's a very key point. Okay, all right. Now coming back to the thing here. So it cannot be reused over here again. All right. The most familiar is going to be the dry cell, which is also called as the Leclanche cell. Leclanche cell is basically named after the dude Leclanche was basically its discoverer, which is what they're mentioning here. Okay, so this is used everywhere. This is your normal pencil battery, LED cell, whatever you want to call it. The cell consists of a zinc container that also acts as the anode, and the cathode is a carbon graphite rod surrounded by powdered manganese dioxide and carbon. So what is going to be the cell here? Let's write down the cell here. So we are going to be having, in this case, the cell is going to be zinc over here. And since it is going to be the anode here, the zinc is going to be becoming zinc plus 2. Okay, all right. The zinc is going to become zinc plus 2. What is the form in which the zinc plus 2 is going to be mainly present? That is going to be ZnCl2. Okay, all right. It is going to be present as ZnCl2. What else is present over here? This is not double line. I should not have put it like that. I should have put it differently. Let me take a different color, make it thicker and put, no, actually no, it's fine. So this is going to be the first part now. This is the anode part right now. In the cathode part, there, what's going to be happening over here? In the cathode part, there, we're going to be having carbon graphite rod is going to be the cathode, surrounded by powdered manganese dioxide and carbon. The carbon is, of course, there for facilitating the flow of electrons. In the sense, the carbon is the graphite rod, which is the electrode over there. So the electrode has to allow the charge or the electrons to basically be transferred. Okay, all right. So what is going to be happening is, in this paste over here, you're going to be having zinc 2 plus, correct? So we will have the zinc cup, this zinc rod over here. Instead of a zinc rod, we have a zinc cup. The zinc cup will slowly dissolve. A tiny bit of the zinc cup basically ends up dissolving into this inside over here. And we will end up having, as the zinc cup dissolves, it becomes zinc 2 plus. So as the zinc cup is going to be dissolving over here, how is that going to be dissolving? It is going to be dissolving technically with ammonium chloride over here, and it will effectively end up becoming zinc 2 plus ions. Let's not call it ammonium chloride there. It will not dissolve in ammonium chloride there. That is actually wrong there. So the zinc will basically end up dissolving and will end up becoming extra zinc 2 plus ions in the solution. Let's just leave them as extra zinc 2 plus. It's fine actually. So we're going to be having extra zinc 2 plus ions present in the solution along with zinc chloride. But the advantage here is this ZnCl2 is present as a solid. All right. If it is present as a solid, what's the advantage? See, have a look over here. In this particular case here, it is calling itself as a paste, ammonium chloride paste. See, ammonium chloride paste. So ammonium chloride is also going to be in the form of a moist paste of ammonium chloride and ZnCl2. What is the purpose of having a moist paste over here? So when you have a moist paste of NH4Cl and ZnCl2, the advantage is the concentrations of zinc 2 plus and ammonium ion. See, if I'm going to be considering this as the reaction, they've given you the anode and cathode reaction here, Nagana. So if you want the reaction to be something which is going to be having constant potential, that is necessary, correct? That's what we talked about. What is needed? Can you tell me, for this reaction, which is given here, anode and cathode, for it to have constant potential, constant voltage, what do I need? Can you turn on your camera, beta? So for that reaction to have constant potential, the dry cells reaction to have constant potential, you have a obvious copy of the dry cells reaction with you. Tell me, which parts of the reaction should you pay attention to if you want to have constant voltage? Which parts can change?
The rods we can anode cathode.
Will the anode and cathode matter? Tell me. If I'm looking at a reaction, Nernst equation. Nernst equation is basically something. What does Nernst equation help us understand? What is the purpose of Nernst equation? It helps us understand how concentration changes affect potential. Correct?
Yes.
Ultimately, that's what Nernst equation tells us. Yes or no? Not just concentration. Another thing which it also gives is how temperature changes also. It can also be used not just for concentration, how temperature change also. Yes or no?
Yes.
Temperature change ka that RT by NF, that part. Okay. Now, in this reaction here, from that point of view, let's start talking about the zinc solid first. Will the concentration of it change? What is happening to the zinc solid over time?
It is dissolving.
Dissolving. Okay. That's why sometimes if you have a battery which is like completely gone, you have it leaking sometimes. Right. Okay, it dissolves. Okay, all right. After dissolving, other than that, what about the concentration? Because technically it is concentration and temperature, right? How about the
Yes.
concentration here? What's happening over here over time?
Decrease.
Hmm? Yes, Kanan?
Decreasing.
Decreases. So if I'm considering the concentration of zinc, okay, you're assuming it is decreasing, correct? Now, let me ask you a very simple question over here. Calculate the concentration of zinc, please. In this case, it's zinc solid, correct? Huh? Calculate the concentration of zinc solid, please. How do you calculate it? What is concentration defined as? Moles per volume. Correct? Huh?
Huh.
Right. Okay. Do I know any mathematical function for a solid which is similar to this? What do I know? What function do you know for a solid? Similar to moles per volume. Can you define density, beta?
Huh. Mass upon volume.
Mass by volume, right? Weight by volume, right? So if I can convert the weight into moles, then I'm done.
Huh.
Correct? So if I know for a solid about information about density, that information about density can be directly translated into information about concentration. Correct?
Yeah.
Because density and concentration, what are they? They are measuring the same thing. Correct?
Yes.
Effectively, just like how we talked about in the previous part, these three are basically measuring the same thing. Different ways of measuring the same thing. Same way here, density and concentration are different ways of measuring the same thing.
Yes.
समझ में आ रहा है मैं क्या बोल रहा हूँ मैम? सो अभी सोचो सॉलिड के लिए डेंसिटी चेंज होता है कि नहीं?
No.
हाँ? Will density of a solid change?
No.
No, no. If I have zinc solid, if I have say iron rod, if I have a tiny bit of the iron rod or if I have an infinite amount of iron, the density is going to be the same, right? If it's from the same source, right? Right? And that basically means what? The zinc solid concentration does not change with time. You understand what your mistake was clearly here?
Yes.
So now, if concentration does not change, now let's have a look again with fresh eyes. So the zinc solid concentration does not change. So if concentration does not change, can it affect my potential?
No.
No. As long as what? As long as temperature doesn't change. So if temperature is maintained a constant roughly, the zinc solid here does not affect my electrode potential. Good. So one guy down. Next. Next. How about zinc 2 plus? What is this guy present as? It's present as ZnCl2.
Huh.
What's the form of the ZnCl2? Moist paste.
Hmm.
Which means what form is it? What's the advantage of solid?
Concentration.
Concentration is constant. So this also is taken care of. You understand where the story will go every time now?
Yes.
You understand why the reactions are so weird? No, I hope. Yes?
Hmm.
Ideally, we would like to keep it simple, but the purpose is going to be to achieve constant voltage. So this is the reason why. MnO2 now, manganese dioxide, powdered manganese dioxide. Obviously solid hai na? So solid na again. Ammonium, how is there ammonia present? Ammonium chloride, what? Moist paste, solid. MnOOH, solid. Ammonia, gas which is going to be trapped on the inside. And when it is trapped on the inside, it is going to be something which is present with what? It is present with ammonium ion. So again, a solid. So you're going to be having the entire thing being something which is going to be purely made up of solid substances. If you're going to be having as many solids as possible, you'll be able to maintain a constant voltage as much as you can. That's the idea over here. So is this properly clear here, Kana?
Yes.
Okay, now let's go to the actual reaction which is happening here and quickly discuss that part out over here. So you're going to be having cathode reaction being MnO2 plus NH4 plus electron giving MnO dot OH plus ammonia. Okay, so effectively what's happening in this particular case is manganese here is in +4 oxidation state, and it is going to be going to a +3 oxidation state in this particular case here. So when it's going to a +3 oxidation state here, you're going to be having a reduction reaction happening in this particular case here. That's why it's gaining 1 electron in the process. At the same time, the zinc is losing 2 electrons over here. So effectively, we are going to be having this reaction multiplied by 2 and then added up. Meaning, what is my final reaction for the dry cell over here? The dry cell's actual final reaction will be zinc solid plus we'll be having 2 MnO2 solid plus 2 NH4 plus in the form of solid gives Zn2 plus in the form of a solid over here plus 2 MnO dot OH plus 2 NH3. In this process over here, 2 electrons would have been transferred. So the number of moles of electrons transferred for this would have been 2 moles of electrons transferred. That's basically the idea. So if the number of moles of electrons transferred is 2, are you familiar with what is meant by N factor, Kana?
Yeah.
Define N factor.
The re- uh, like in acids, replaceable hydrogen atoms.
How about for redox?
Moles of electrons.
Good. So effectively, you're going to be having N factor in terms of redox there. You're not exactly on the right path, but you're on the right path to an extent. So you're going to be having N factor being defined as N factor for redox. The best way to define N factor for redox reaction is number of moles of electrons transferred per 1 mole of substance. That's basically the idea over here. So number of moles of electrons transferred for every 1 mole of substance is basically what is going to be meant by N factor for a redox reaction. Now, what's the best way of doing this? Balanced reaction. If you have it already, check the balanced reaction and you'll get the answer directly. So in this case, 2 moles of electrons are transferred for the overall reaction, correct? So for zinc, what is the N factor? 2. And for this guy, N factor is 1. For this fellow, N factor is 1. For this fellow, N factor is 2. For this, N factor is 1. And for this, N factor is 1. You understand the idea here?
Yeah.
Okay, all right. Now let's continue on. So this is the reaction over here. We are going to be having number of moles of electrons transferred. Okay, that is also covered. Okay, ammonia produced in the reaction forms a complex with zinc 2 plus. So they're telling you that the zinc 2 plus over here is actually going to be complexating with the ammonia over there. I actually assume that it's going to be basically present with the NH4 plus, but I was wrong over here. The actual reality is it's going to be complexing with the ammonia there. So this zinc 2 plus which is produced here is actually going to be complexing with the ammonia to effectively form this ZnNH3 twice. Is not correct. That doesn't make sense. ZnH3 4. Yeah, they have given 4 only. So that's correct there. So we're going to be having ZnH3 4 times 2 plus. Sometimes the reading itself I'm doing wrong. ZnH3 4 times 2 plus is going to be the complex formed here. So why did I stop there when I thought I read 2 there? Main reason is because zinc 2 plus only forms tetrahedral complexes. So the moment I saw ZnN, I thought I saw when I was writing ZnH3 2, I thought I saw 2 there. I realized, Anyway, so coming back to the point here, that is something you guys have coordination compounds also, Nagana.
Yes.
So you need to know about that point also. I'm hoping that you already knew it. Yes?
Yeah.
Good. Okay. Now, in this case, the cell potential here is going to be nearly 1.5 volts. That's just an information. It is good to have that information because it's available in NCRT. You need to know this piece of information. Absolutely. Okay, that's why you need to know this complex also. This complex here is a tetrahedral complex. Okay, and it's a D10 tetrahedral complex. All right. Next, the mercury cell. We're going to be having it suitable for low current devices like hearing aids, watches, etc. Consists of a zinc mercury amalgam as anode. So zinc mercury amalgam, now we are going to be having zinc dissolved in liquid mercury. When you're going to be having zinc metal solid dissolving in liquid mercury, you'll end up having the final mixture is going to become an alloy, a hard alloy, which is called as zinc amalgam in this particular case here. That zinc amalgam is going to be the anode over here, and a paste of mercury oxide, HgO, and carbon acts as the cathode. The electrolyte is a paste of KOH, again paste. What's the purpose of the paste? So that the substances are present in something which is closer to a semi-solid state. What's the reason to have a semi-solid? So that we'll be able to have a proper cell where the potential is going to be nearly constant over time. Why is that necessary? Well, I mean, why is solid necessary for that? Because if solid is taken, concentration will remain constant. Okay, so electrode reactions are given over here. Same type. The zinc is effectively going from 0 to zinc plus 2 here. And we are going to be having, in this particular case as well, 2 electrons being lost. The HgO here has mercury in plus 2 here, and it is going to become mercury in oxidation state 0 by gaining 2 electrons in the process. So we can directly add these 2 reactions up to get the final reaction for this one over here. The final reaction for this looks like this, where we are going to be having it as, or the overall reaction is going to be simply adding the 2 of them up. So zinc amalgam, which is going to be a solid in this particular case over here, is going to be reacting with 2 OH minus. Where is the OH minus coming from in this case here? It is a paste of KOH and ZNO. So the KOH is going to be something which is going to be producing this over here. So this is solid in the form of KOH. Okay. Along with what else is the other reactant here? HgO is going to be the other reactant, which is of course going to be a solid as well over here, solid paste of that over here. And we are also going to be having water as the other reactant in this case. Now, when you're talking about water over here, that is where things are going to be getting a little bit interesting. Water, as you know, at a given temperature is having constant density as well. So in this case here, the water will of course be, if it is present in the liquid form over here, so its density is going to be more or less the same, and it is not going to be changing as well. So if the liquid's density is a constant, it will also not be affecting what the potential of the cell over here. So this liquid is also perfectly fine. All right. And lastly, what are the products over here? We're going to be having zinc oxide, which is a solid over here. So zinc oxide solid is of course going to be something where there's no problem. Water, which is going to be a liquid as well, is not going to be having any issues over here because it's also having a constant density. Mercury liquid is also perfectly fine. And the OH minus, of course, what is that present as? That is of course present in the form of KOH. So this is going to be also a solid. KOH is going to be the source of this. So this is your overall reaction here for this cell. And as you can see here, you're going to be having this cell being something where we have all of the systems which are playing a role being in solids or liquids, which means their concentrations are constant. So if the solids concentrations are constant, the cell potential becomes constant as well. So this is going to be for your mercury cell here. Let me copy the next part as well so that the next part also can be directly discussed. Mercury cell, I think this is more or less the last bit over there. Next is going to be the secondary batteries over here. So let me copy that part. So when you talk about the secondary battery, beta, how will that work? What is the purpose of a secondary battery? The purpose of a secondary battery is to run both ways, right?
Yes.
Today till what time are you free, Kana?
Sir, you can take. You can teach.
Okay. Okay. All right. So the secondary cell here is something where we are trying to do both the electrochemical part and the electrolytic part. Correct. We have to charge it in both ways. Now, if we are going to be having charging in both ways to be considered over here, then we have to design a cell where that can be done properly. That is the reason why secondary cells are definitely more costlier than primary cells, because it can do both and it is far more efficient at basically utilizing space. So usually when you're going to be having rechargeable cells, they are inherently going to be more expensive. So let's start off with the lead storage secondary cell over here. That's the one which we have over here. So a secondary cell is something where you can recharge it after using it for some amount of time by passing current in the opposite direction. So it can be used again. A good secondary cell can undergo a large number of discharging charging cycles. Right? So effectively, a good secondary cell is something which can be used many times. So that's the purpose of a secondary cell. Okay, all right. So let's continue here. The most important secondary cell is the lead storage battery. This is something which may be changing, because the fact is the most important secondary cell of the current modern world is not the lead storage battery. What is the most important secondary cell now? Beta, are you still on the call?
Yeah.
So, are you living in the modern world? What is the most important secondary cell in the modern world now?
Mobile.
What is it?
Mobile phones.
What is that? What is that? What is that?
The battery of.
Lithium-ion cell. So the most important one currently, this statement alone, I will not agree with this statement. The most important current one is actually going to be lithium-ion. Secondary cells, the best one currently, the most important one is lithium-ion cell. Anyway, coming back to this now. So lead storage is our syllabus is one, which is designed a long time back. So let's start off with lead storage. It consists of a lead anode and a grid of lead packed with lead dioxide. Okay, all right. As cathode. So effectively, lead anode is going to be taken and a grid of lead dioxide as cathode is taken. A 38% of solution of sulfuric acid is used as an electrolyte. Okay, so 38% solution, they are being very specific over here. I'll explain why they are being very specific in a minute when we are discussing the reaction. Okay, so the cell reactions when the battery is in use is given over here. So what is happening over here is you're going to be having anode is going to be lead here. So we are going to be having lead solid reacting with SO4 2- aqueous. Where is the SO4 2- aqueous coming from? This is of course coming from your sulfuric acid. All right, so from sulfuric acid, you're going to be having this coming. This is basically going to be giving me PbSO4 solid, which is going to be a white salt, white precipitate. You'll actually have it as a salt precipitate on the cathodes on the inside over there. Plus, of course, we'll be having 2 electrons being kicked out. Okay, now the next thing over here is going to be when you're going to be considering the anode reaction over here, this is basically something where oxidation is of course happening. Now, when we're going to be considering the cathode reaction next now, in the cathode here, the opposite has to happen, the acceptance of the electrons has to happen. So when we talk about the cathode reaction there, what has to happen over there is the PbO2 here, which is in solid form, has to react with my SO4 2-. Of course, in this case, is also going to be in aqueous form over here. Now, as you can see here, the reaction is also having a 4H plus over here and 2 electrons. So let's talk about what is happening here. Why do we have all of this 4H plus 2 electrons, all of this stuff? Why is it coming in actually? Now, when you're going to be having the reaction here, let's break the reaction down quickly here and just talk about it. So PbO2, the solid is going to be reacting with sulfuric acid aqueous from H2SO4. All right. And we are going to be having the reaction here producing again PbSO4, which is a solid. This is the reaction. Actually, this is sufficient. And of course, we will end up having water as well. But let's talk about why the water is supposed to be there. So PbSO4 solid is produced over here, correct? So in this case here, this is going to be the same white precipitate, nothing different. So this is technically going to be something where you can think of it as a con-proportionation reaction. So why is it a con-proportionation reaction? Because technically speaking, we are going to be having Pb becoming Pb plus 2, and we will also be having on the other direction there Pb4 plus also ends up becoming Pb plus 2. So in this case here, as you can see, the Pb plus 4 here is actually becoming a Pb plus 2. So effectively, we had a Pb0 becoming a Pb plus 2, and a P plus 4 also ends up becoming a P plus 2. That is the overall essence of the reaction. So this type of a reaction can be thought of, and it is called as a con-proportionation reaction. You're familiar with disproportionation, yes, Kana?
Oh, yeah.
So now let's dive into, you're familiar with disproportionation or not, beta?
Disproportionation.
हाँ.
हाँ.
ठीक है. Okay, so in this particular case here, when you're going to be having this reaction happening over here, what is going to be happening in this particular case here? You're going to be having, as the process happens, there is, okay, I have to show the balancing part here. Na? Balancing ka dikha deta hu. So here there are 2 oxygens extra over here. We're going to be having, in this particular case here, water has to be added to balance out the oxygens. So 2H2O, so you'll effectively end up having a 4H plus on this side to balance out the, 2H2O over there. And of course, you're having plus 4 becoming plus 2. So you have to accept 2 electrons as well. So you're going to be having this as the reaction here. So you understood the balancing as to why I added 4H plus, etc. It's acidic medium balancing. I think we had discussed acidic medium balancing in one session, correct?
Yeah.
Now, so in this case here, The overall reaction has been beautifully given now. Have a look at the overall reaction here. So we have it as something like this. Now tell me if the overall reaction is in the discharging mode, which is forward direction. So forward direction for this reaction here, the forward direction is basically electrochemical, and it is called as discharging mode. Okay. And the backward direction is going to be something which is going to be called as the charging mode. Okay, so in this particular case here, we are going to be having the cell here, this electrochemical cell over here is something which is going to be meaningful in the forward direction, whereas the backward direction, which is the charging mode, is actually what kind of a cell? An electrolytic cell. You understand the principle here, Kana?
Yes.
Okay, good. So now let's continue on over here to the next part here. So on charging the battery, the reaction is reversed and PbSO4 solid on anode and cathode is converted into Pb and PbO2. Effectively, what they are telling you is the exact full reaction is going to be happening in the opposite, in the charging side. You understand the principle there? That is the exact full reaction. Now the exact thing will happen in backward. Over here as well, the exact thing will happen in the backward direction here. And over here, this exact thing will happen in the backward direction over here.